Okay, welcome this third live stream. Here we go. So, where we left off last time is this. We were working, and I finished making it actually work after the stream was done, to write a system that turns a program written in 6502 assembly that uses external registers to wiggle the interesting pins on the CPU into a test plan, which looks like this. So it says for every cycle what address it accesses, if it's a read or write, if it's a read, what is supposed to come back, and if it's a write, what it is writing. And I've also put in a comment the information of where from the test program that information came. So that allows us to know exactly what the program needs to do in each and every cycle. So what we want to do now is turn this, as well as the representation of the program itself, of the memory structure itself, into an actual running of our emulator, so that we can compare and make sure that it is running correctly. Okay, so that's a different project. Okay, so that's our emulator. That's where we left off. What we obviously need is a main. So let's do just that. Let's write So let's write, I created a makefile, verify CPU program. That will be our main for verifying the CPU. So here goes. First thing we need is we need to read in. Okay, first thing we need is a main. And we'll probably need a few parameters, so argc and argv. And the first thing we need is we need the name of the test program we need to run in memfile, and we need the name of the test plan we're comparing against. Okay, here goes. We prepared, it wasn't here though, but it was in the test program. Okay, so we had under test harness perfect 6502 read mem. So we're going to include that. And that gives us an, no, that's the wrong file. We want readmemh. We want a class called readmem. So readmem reading 8 bits at a time. That's the memory image. And we're going to give it argv1. And we want the test plan. The test plan looks like this. Test plan MOS. It goes 8-bit for the 8-bit for the flags, and then it's least significant to most significant. So 8-bit for the flags, and then 8-bit for the data, and then 16-bit for the address, and 4-bit for the type. That's the test plan, and we initialize that from argv2. Go. We're set to go. First, let's read in the memory image and initialize the memory. So, the way we interface with the emulator is by supplying it with a bus class. So we'll make the memory a member of the bus class. So we'll just define it in this file, a test bus, and that will have an std byte, std array of std byte of size 65536, so 64 kilobyte memory. And to initialize it, we'll move this in there. So test bus, we'll get memory image, okay. Here goes. We've got the memory image. We need to read it in and initialize the memory from it. We already have a template that does that in the test simulate MOS. Here we go. So we need this. While memory image read line, and pretty much this line as is. So memory at memory image address is memory image index 0, because that's the only one there is. So that initializes the memory. That should work. Okay. So let's initialize the bus. And there's one more thing. We need the bus to derive from the bus we defined. So public bus. Okay. That won't compile, but let's test anyway. We go make. It says can't include readmem.h. That's a makefile issue. We'll tell it that -i, the include directory includes one project up, test harness, perfect 6502. Okay, bus.h isn't found because I misspelled it, and span in namespace readmemh. Okay, readmemh. Okay, we need a compilation flag 6x flags equals std equals c plus 20. Shadows a parameter there, right? We gave it the same name. So let's call it memory image file. Cannot convert data container to std array. They're right. Okay, so we won't do it std byte. We'll call it uint8t because it's simpler. No matching function to call test bus. Okay, so we finally get into the interesting errors. No matching function to call test bus. Where did I do that? Here, argv1. We'll get in there, don't worry. Cannot declare variable best to be abstract type. That's it, we got it. So, what it says is we derived test bus from bus. Bus defines read and write as pure virtual functions. If we want to actually define an instance of test bus, we need to provide an implementation for these two. But luckily, that's very simple. We just go read is return memory at address, and write is memory at address equals value. So this ought to do it. Almost. Okay, we need to link with it's called readmemh. And that's the thdir. So we'll define thdir as test harness perfect 6502, and this way we can change this into thdir. And that's it. Let's run it. Segmentation fault because I didn't give it anything to work on. So we go test harness perfect test program mos mem, and test harness perfect 6502 test plan mos mem, and it initializes the memory and then exits. It doesn't do anything, but it works. It doesn't crash. Great. Okay. So what we need to do next is to run the CPU. And we can do that by simply, we have our C6502 CPU, so we instantiate that. And it needs a bus as a parameter, so we give it that. And then we can do CPU run CPU. And that should result in an infinite loop. CPU C6502 was not declared in this scope. why? Oh, because we didn't include it. That makes sense. And we have an infinite loop, which is kind of expected because we didn't do anything. So this is the point where we've laid out the path and we can start filling it in with meaning. So let's see what we do. First of all, let's assert at the CPU if we hit a command that is undefined. So we go to the c6502.cpp and we have our switch where we handle the opcodes. And what we want is default cair unknown command current opcode abort. So right away that should give us some feedback on what's going on. And of course it complains about a bunch of stuff missing. Okay, there's one problem. What happened is that it printed our unknown command, but it printed that as a character. So instead of getting its value, we got it as an ASCII thingy. So we'll just convert that to an integer. Better. So unknown command 5e aborted. Let's also okay, but so that's a start, but that's on the CPU part. But remember, the only reason we are doing the verification is because we want to make sure the CPU is doing what it is supposed to do. So the first thing, so we want most of the verifications to happen on on this side, on the verify CPU side. And the only interface verify CPU has towards the CPU, because remember, the very thing that during the first live stream was a huge plus of simplifying the code, that we just enter the CPU and we never leave, and we can just go on a loop and handle one opcode after the other. And the code is very, very simple and very, very nice. The same thing that allows us to do this on the CPU side means we now on the bus side need to work very hard, because we call run CPU and it never returns. So we need to do everything we want to do through being called through read and write. I am going to handle that in the next video. So the next video will be all about making that easier. But right now, let's handle this as is. Maybe it's a good time to point out that I have a pattern page. Check it out. But okay, so how will we handle this here? So first thing, we need to pass not only the memory image to the bus, to the verifying bus, but also the test plan. So we will actually give it argv2 as well. And this will go into the to the bus as well. So we'll have a second parameter to the constructor, which is the test plan file. And we will initialize the test plan from the test plan file. Okay. So that's a start. Now, if we look at the test plan, at the actual test plan, we see that it starts at FFFC. But that's not where the CPU execution started. The CPU execution started somewhere else. So what we're doing is we're defining the test as beginning when the CPU reads from FFFC, which is the reset vector. So when the CPU finally gets to read the reset vector and start execution, that's when we start checking the CPU. Until then, it gets an almost free pass to do whatever it likes. However, it's not a complete free pass. So let's give it, I don't know, 50 cycles to start executing. So what we need to do is we need to keep a state inside the test bus, how many cycles until we begin execution. So size t, cycles until start, and we'll just initialize it to 50. And what happens here is that if we do a read, we check cycles until start, and if it's bigger than 0, it means we have not officially started yet. So uint 8t ret equals. So we will read the memory because that's what we do, and we will return. But in between, if cycles until starts is bigger than 0, then we check what the address is. If the address is equal to FFFC, then we're essentially started. Then so cycles until start equals 0. FFF reset vector read detected, and we've started. Else, cycles until start, we need to subtract 1 from it. But if after subtracting 1 it is 0, it means the test has failed. We have failed to get the CPU to read the reset vector. So we go cr CPU failed to read the reset vector, and we abort. Okay. Now, there's another tiny issue. We need to actually reset the CPU, because we haven't written any reset handling code in the CPU at all. So let's talk about that part. So the CPU is composed of 2 parts, a .h and a .c. So first of all, we need sort of external legs that in which a external program can tell the CPU whether it is in reset mode. And while we're at it, we have reset, and we have IRQ, and we have NMI. IRQ is interrupt request. NMI is non-maskable interrupt. And we have ready, which is a signal that allows an external system to freeze the CPU, not handle anything. And we have one more signal called SO, which stands for set overflow. Set overflow is a 6502 specific signal. It's this one. And what it does is it externally can tell the CPU to set an internal flag. So no complete handling of it right now. We just define it and we set them all to false, which is technically the reverse of what the actual 6502 does. The actual 6502, they're active low, so they're by default set to high. But I'm not going to complicate my own life by doing this reverse logic. So false it is. And then I need accessors. So I need set reset bool state. And then set IRQ, NMI, ready, and SO. So, what do they do? They're actually fairly simple. Let's see, 6502. They go reset equals state. Okay, let's see if we still compile. Of course we don't. Line 22, need semicolon. Okay. So, now what we need to do is on the bus side, we need to make sure that we actually reset the CPU. So, if we go back to our verify CPU, we go initialize the CPU, go CPU set reset true. And now we need cycles until start. Okay, so we'll const expr size t start grace cycles equal 50. So if cycles until start is greater than 0, we go if if we've gone 2 cycles with the CPU in reset mode, we'll do CPU set reset to false. So we give it 2 cycles and then we take it out of reset. Yeah, that's a good start. Let's back that up with Let's print when the state changes. So reset IRQ NNI ready and SO. And it says I don't have a CPU. Okay, I think it makes no sense to store the CPU inside the bus. Instead, we'll go class C6502 and we'll get C6502 pointer CPU. We'll just pass it as a parameter to the bus operations. Which of course we will need to also reflect here. So override now if I try to compile, it will go you need to line 28. This is a pointer. Okay, and on the CPU side, I need to pass this parameter. But if I'm already changing the parameters on the CPU side, I don't want to. Right now on the CPU side, what happens is that we directly call the bus on several occasions. And I don't want to do that. I want to go through an intermediate function in the CPU. Will be very clear in just a moment why. So I'm just going to change bus dot. I'll just erase that everywhere. Okay, and now I'm going to add a private function to the CPU that goes void read ADDR address bool sync equals false, and not void uint 8t, and void write ADDR address uint 8t data. Okay, implementation goes like this. So at its base, it's just a pass through to the bus, but we will do something more interesting with it in a second. So if you're trying to read, we go bus.read this address sync. And if we try to write, we go bus.write this address data. So a pretty straightforward pass-through. And now it should compile. Right, we need to declare that it's a member, it's a method. C6502. Default argument given, right. Okay. So far we haven't changed anything. This is where we begin to actually implement the signals. In particular, if we are in reset mode, then we need to stop whatever it is we think we're doing and do something else. We will do it after the read. So we will go uint 8t result equals and then if we're not in reset, we just return result. And if we are in reset, we throw a class called CPU reset, which is an internal class. It doesn't have anything except it exists. But it will stop whatever it is we're doing. Now, for write, things are a bit more nuanced. We go, if we are in reset, we turn our read into a write. And then we throw CPU reset. Otherwise, we just perform the write. So let's see how that works. CPU H write. Terminated after throwing an instance of 6502 CPU reset. So what we need now is to catch CPU reset. We do that in the main loop. In fact, that is the reason I separated handle instruction from the main loop. So we do try, and we do catch CPU reset. And if we are in CPU reset, we, at this point, don't do anything. Let's just do this, but this will prevent CPU reset set high, CPU reset set low, and then we go the unknown command 5e. That's cool. Okay. So what we need to do now is write the reset sequence here. So reset sequence goes here. What is our reset sequence? Let's write it. C6502 reset sequence. We need to set reg PC low from read FFFC, reg PC high read FFFE, and that's it. So we read the reset vector, and we're ready for the next instruction. Now, I should point out, this is not the 6502 reset sequence. The reset sequence is longer and does other thing. But this is just enough to pass the stage of the execution we are currently in. So, we go reset 1, we go reset vector read detected, okay, here I have a bit of a problem. Okay, I know I will fix it. Verify CPU. If address equals and okay, so let's keep a global state. Bool CPU in reset equals false, and then we go set reset true, CPU in reset equals true, and then we go set reset false, and CPU in reset equals false. Then we go and not CPU in reset. So we only consider the test started if we're reading from FFFC after we've released the CPU from reset. Doesn't like this for some reason. CPU in line 57. Yes. Okay. We go reset 1 after throwing an instance of CPU reset that was not caught. Okay, is right. So we need to change the loop here a little. Reset. We do the reset sequence. If reset, else. Okay. Okay, so reset goes high, reset goes low, and then reset vector read detected, and then unknown command 7F. Let's make the at let's print the address where the unknown command happened. F1, F5. So first of all, let's check whether F1, F5 is indeed where we expected to read. So let's go to the test plan, and we see that it isn't. So we're obviously not reading the reset vector correctly. We were supposed to go to 06 F5, and instead we went to F1 F5. So we start a debugger, right? We first of all we add the debug symbols. Okay. Okay, so let's see what we have here. This is the bus. Reg A, Reg X, Reg Y, Reg SP, Reg status are all 0. PCH is F1 and PCL is F6. So let's break point where we're reading the reset vector. So we want break C6502.cpp at line 61. We perform an exception. Perform an exception. Okay, so reg PCL is F5, and now we go to it's the wrong address, FFFD. Okay. Better. Unknown command A2 at 6F5. So what we see is that we have successfully passed reading the reset vector. We have gone to 06F5 and we are reading A2 command, which is LDX immediate. And at this point, we can even skip the data sheet. We can just immediately start implementing. So we can go A2 op LDX ADDR mode immediate. And it doesn't have LDX, so we say fine, LDA we copy that to LDX, and we read that into X. Op LDA, op LDX. Done. Unknown command 9A at 6F7. 6F7, 9A, that's transfer X to S. Again, we don't even need the data sheet. We can go (9A) op transfer XS and ADDR mode implicit. Of course, this time I'm missing both transfer X to S and ADDR mode implicit. So we'll fill those in. ADDR mode implicit and op transfer XS. Actually, since transfer XS never needs an address, we can just not define here one, and then not bother with ADDR mode implicit. No, I'm gonna bother with ADDR mode implicit anyway. The reason I'm gonna bother with ADDR mode implicit is because we need to consume a program counter. We have a bus operation we need to perform. I'll show you in a second. It's going to be very clear in a second. Okay, so transfer XS. So we have ADDR mode immediate. We go ADDR C6502 ADDR mode implicit, and we just go return something. We don't do any operation, we just do something. Okay, just a second. We need also the op void C6502 op transfer XS ADDR. And here what we do is reg transfer X to S. So reg S equals reg X. So that's the operation. And now line 129. Okay, unknown command 40 at 701. So it reached all the way here. Push a LDA. Obviously, it didn't, right? Obviously, it didn't perform the right operations. But we never followed it. We never verified that it's doing the right thing. So that's what I want to do really quickly now. Here's the thing. If we go to the verify CPU, we have this part, which is we're still waiting for the program to start. But if the program has started, we need to verify that this is the operation that should have happened now. So what we need to do is we need to read another line from not memory, from the test plan. So we go bool valid equals test plan dot, we had it copied somewhere in simulate MOS. Read line. And now we need to verify that the line is okay. So we have essentially three things to verify. If we look at how the test plan is built. First of all, this is a read operation. So we need to verify that in the test plan, that too was a read operation. So we need to say check that a test plan 0, that's the first byte, equals 1. Is 1, and if not, read operation where write was expected. And we provide the address and the result. Okay, so that's the first check. The second check, if we got here, it means that this is a read operation. So we want to make sure that we're reading from the correct address. So the correct address is, so we go test plan 2 is supposed to be identical to ADDR. Otherwise, read from wrong address. And the last check is to see that the data we got back is the data we're supposed to get back. Otherwise, probably some write that happened before didn't go as expected. So we go test plan 1 is the same as res. Read wrong value from memory. ADDR res. Okay, let's implement check. It's a fairly straightforward function, actually. Goes like this. Check. We need readmem defined something called data container. Yeah, okay. Readmem support data container expected. Readmem support data container actual. And then a message ADDR address and uint8t data. And then we just do this. We need one more thing. No, we don't need, we have it. std cr validation failed on plan line number. The plan, the readmem support can report a line number. Can it? Well, it can't, but we can make it. So okay, so we want the message. Expected got actual at actually we want here to switch to hex. So this will be decimal and this will be hexadecimal. At address data data, and we abort. And I believe that this should fail earlier. ADDR was not declared, line 49. Res was not declared. That's because we call it by an unreasonable name, ret. Okay, I can leave that. Okay. Invalid operands of type const char 32 and IOBS to binary, line 67. Okay, line 67, we want a test plan okay. I added it at the wrong line. Okay. Let's move it here. Read man h. Public. This should do it. Or not. Okay. It's time to debug again. Let's break at a test bus read. Okay. We go this and ret is F5 and then read line hangs. Why does read line hang? Okay, we have a problem with the parser. Next datum. Okay, so that's the reset vector. Parse hex number. So underscore FFFC underscore F5 underscore 01. Okay, so that's fine. And now line equals O. I don't advance if I have a separator. So let me just very quickly fix that. I no longer remember. Okay, so I need to, it's a span, so line equals line sub span 1. Okay. Okay. Validation failed on plan line 1, and I need why is there okay, so a couple of questions. First of all, why is there no space? Okay, sorry, now it's clear. So that's one mystery solved. The other is check, go if actual different from expected. Let's do it the other way around. If actual is equal to expected, return. Validation failed on plan line 2. Read from wrong address. Expected FFFD got FFC. Data, okay. The data again needs to be converted to int if we want it to actually show up. Data A5. Okay. So, test plan, line 2. Should have been working, but you know what? I think I've held all of you long enough. This is the structure. So there are a few tiny bugs, but what we see is that we can run the CPU and compare what it actually does with what we expect it to do. And this way, we make sure that it stays on track. Anytime it deviates from track, even by a little, we stop it. We get concise messages saying where in the test plan the problem is. And I think I'll demonstrate that in the next video, in the next time. So thank you for joining me.